Hello, I'm Zhou Longyu, a PhD student at Johns Hopkins University. Today, I'm glad to share our work, NetLock fast centralized log management using programmable switches. This is a joint work with people at Johns Hopkins University and the University of Michigan. So in this work, we introduce a new mechanism to do log management to achieve both good performance and flexible policy support. Nowadays, more and more enterprises move their workload to the cloud, which increases the demand of database services normally provided by public cloud providers like Amazon, Microsoft, and Google. Log managers are a critical building block of cloud databases. They are normally used to mediate the access to the resource and ensure serializability. Now let's take a look at a simple transaction. To begin with, a client needs to go to the log manager and acquire the log from the log manager. After he gets the log, he can then access the resource and do some read or write. After he finishes, the log then can be released. Recent years, some works about in-memory databases and RDMA networks have significantly improved the performance of distributed transactions. As a result, the overhead of dealing with the log manager has become the major component for end-to-end performance. So we wonder, can the log manager be faster? Besides the performance, another important factor for log managers is policy support. With global knowledge, traditional centralized log managers can provide flexible policy support such as starvation-free, priority, and performance isolation. But they often fall short as the performance and are always bottlenecked as the server's capacity. While decentralized log managers can provide better performance, they cannot efficiently support the policies. Among the decentralized log managers, DRTM proposed in SOSP 2015 uses a blind fill and retry method to acquire logs, and it will introduce high client CPU usage. And some works applied exponential backoff to reduce the CPU usage, but it will increase the latency. And there are also works using distributed queues to emulate centralized log managers in order to avoid starvation, but it will introduce extra network round trip, and which will lose the benefit of high performance. The most recent work, DSLR, which is proposed in SIGCOMM 2018, applied Lamport's bakery algorithm in an RDMA network, and it can avoid starvation and therefore provide high performance, but it can still not support other policies. So can we have both good performance and flexible policy support? We wonder, what if we replace the log manager server with a programmable switch? Here is a simple comparison between a switch-based log manager and a server-based log manager. We can see a switch can provide much higher throughput compared to a log server, and the switch here is not even saturated. And that might help us eliminate the bottleneck of the centralized approach. Here is a brief introduction to the protocol-independent switch architecture, which is normally used by the programmable switches nowadays. When a packet comes, it will go through the programmable parser and the programmable match action pipeline. The programmable parser is to pass custom key value fields in the packet. And the programmable matrix pipeline allows us to access the data at the line rate. With that, we want our system to have good performance, including high throughput and low latency. And we want it to provide flexible policy support. Well, it may seem that these goals can be directly achieved by using high-performance switches and a centralized approach. However, there are two challenges to realize the system. Firstly, the switch has very limited memory to store the logs. Although the size of the log information is much smaller than the size of the actual data, it can still exceed the switch memory for the large-scale databases. Secondly, although programmable switches are becoming more and more powerful, the functionalities they can provide are still very limited. Here we show the architecture of our system. NetLock processes log requests with a combination of switch and servers. And the switch only needs to store and process the requests on popular logs, and the server will help with the rest of the logs. And NetLock is also incrementally deployable and compatible with the existing data center networks. Before we talk about how we handle the requests, let's first look at the packet format. The NetLock request packets are specified by a reserved UDP designation port. And the essential fields for NetLock applications are organized as part of the UDP payload. Here are some essential fields. The action type is used to specify whether the packet is to acquire a log or release a log. And we have log ID. And the log mode is used to specify what type of the log the client wants. And we have the transaction ID. When a packet comes to the switch pipeline, we will check the log ID and decide what operations to take. For each popular log, there is a circular queue to store the log requests, and we use some extra registers to keep the head pointers and the tail pointers. For example, here there are 6 requests queued for log A, and the head pointer is at 1 and the tail pointer is at 7. To better utilize the registers, we let all the logs to share a large queue and keep some extra registers to store the left boundary and the right boundary. And the boundaries can then be modified in the runtime. In this way, the log can have a queue with a flexible length according to its popularity. As the switch memory is limited, we co-design the switch and the servers, and we store only popular logs to the switch memory. When assigning memory for logs between the switch and the log servers, we want to process as many log requests in the switch as possible in order to reduce the number of log servers we need. Here is a simple example. We have 2 logs. Log 1 has a contention of 2, and the log 2 has a contention of 1. And the switch can only store 2 requests. With the left allocation method, 100 requests per second for log 1 will be sent to the log server, while in the right allocation method, only requests for log 2 will be sent to the log server. And it's only 10 requests per second, which is much better than the left allocation, and it's also what we adopted in the NetLock. We formulated the problem as an optimization problem and solved it. Please refer to the paper for more details. Also note that clients doesn't need to know where the requests will be processed when sending the log requests. Then we show how the shared logs and the exclusive logs are handled in the switch pipeline. Here there are 4 read requests and 1 write request coming. Since the queue was empty, the first read request gets granted directly. When he finishes and releases the lock, we then need to notify and grant the following locks waiting in the queue. Since the switch normally only supports 1 memory access to 1 register array upon 1 packet, we use resubmission to achieve that. The packet will then be resubmitted to check the next request in the queue. Then we find out it's an exclusive request waiting to be granted. So we will notify him and grant the lock. After the write action is also done, we will again release the lock and do some resubmission to grant the locks until we meet an exclusive lock and the tail of the queue. There are 3 major policies NetLock can support, namely starvation freedom, service differentiation with priority, and performance isolation. And here we briefly show how these policies are supported in the switch. We store the requests in a first-come, first-served queue, which prevents a later request getting processed before an earlier request, and avoid starvation. It's challenging to support priority queues in the switch as always. So in order to support the differentiation with priority, we store requests with different priority in separate queues, and we allocate 1 queue in each stage for 1 priority. And the switch only stores the high priority requests, and the low priority requests can be offloaded to the local service. For the performance isolation, we also maintain a counter as a rate limiter to enforce a quota for each tenant to achieve isolation. Let's now go to the evaluation part. Our testbed includes a 6.5 Tbps barefoot Tofino switch and 12 servers with an 8-core CPU and a 40G NIC. We compare our system with the state-of-the-art approaches, DSLR, DRTM. These 2 are both RDMA-based approaches. And we also compare our system with a programmable switch solution, NetChain. We use a micro benchmark and a TPCC workload with different contention level to evaluate our performance. Through the evaluation, we want to answer 4 questions. First, how fast can NetLock process lock requests? We will answer this question using the micro benchmark. And second, we want to see the benefit of NetLock over existing solutions when processing transactions. And we will use TPCC workload to demonstrate our benefit. And can NetLock provide flexible policy support? And also NetLock's reaction to the failures. In this talk, we will only mention the first 3. First, let's see how fast can NetLock process requests. With the micro benchmark scenario, as we increase the sending rate at clients, the throughput grows and the latency keeps unchanged. So we can see the 12 servers in our cluster cannot saturate the switch, which can process billions of packets per second. Here is a comparison between NetLock and existing solutions. And we use TPCC workload in this scenario. The left figure is for lock throughput, and the right figure is for transaction throughput. In both cases, we can see that NetLock outperforms other approaches a lot and improves the throughput by up to 18 times compared with DSLR. NetLock also has very low latency. It has much lower average latency as well as tail latency compared with the other three solutions, and it reduces the latency by up to 20 times compared with DSLR. Now let's see how the policy works. First, we show the service differentiation. Here we have two clients, one client with low priority and the other client with high priority. When the differentiation is not enforced, two clients get similar throughput because we treat them the same. After we enforce the differentiation, the high priority clients get much higher throughput compared with the low priority client. We also show performance isolation. We have two tenants. The tenant 1 has 7 clients, and the tenant 2 has 3 clients. And also tenants are sending with the same sending rate. Before we enforce isolation, tenant 1 gets more than 2 times throughput compared with tenant 2. But after we enforce isolation, we can see two tenants get similar throughput. So to conclude, NetLock is a centralized approach to realize lock management in the network. And it co-designs programmable switches and servers to avoid the limitation of the memory size. And the evaluation shows that NetLock can provide high performance and flexible policy support. That's all. Thank you. Please feel free to reach to us if you have any questions.